The next example of nucleophilic addition reactions of aldehydes and ketones is the reaction of the cyanide ion with aldehydes or ketones to give what's called cyanohydrins in what's called the cyanohydrin formation reaction. Let's draw a general scheme for the reaction in order to understand what's going on. So if you take a general structure for aldehydes, so that's a general structure for aldehyde, and now we react it with a catalytic amount of the cyanide ion in the form of sodium cyanide, for example, or potassium cyanide in the presence of HCN. So catalytic cyanide ion, HCN, we have a general aldehyde here, and the product is the corresponding addition product, which is called cyanohydrin. When carbon has a cyano group and hydroxyl group attached to it, it's called cyanohydrin. So this product is cyanohydrin. It's an example of a nucleophilic addition reaction on aldehydes and ketones in general. So what happens is that the cyanide ion will come and attack. So we can write actually the cyanide ion here. So the cyanide ion will come and attack. And remember the Burgi-Dunitz angle, the angle of attack of nucleophiles of on aldehydes and ketones. So the nucleophile attacks that carbon, okay, and the carbon-oxygen double bond simultaneously breaks. And if that happens, we get the nucleophilic addition product. So that intermediate alkoxide, which is the product of this nucleophilic addition reaction, as we have seen before in the general representation of the attacks of nucleophiles on aldehydes and ketones, the intermediate alkoxide then gets protonated, and in this case it gets protonated by HCN as a proton source. So we can write HCN like that, and then the alkoxide picks up a proton from HCN in a protonation reaction, and this HCN bond then gets broken, and the electrons of that hydrogen carbon bond that has been broken are now gone or released on carbon. Now this gives the final cyanohydrin product with release of the catalyst, if you like, because we use the cyanide ion as a catalyst, a species in catalytic amount less than 1 mole, if you like, in general relative to the reactant. So this step, this protonation step, releases the product plus the cyanide ion regenerated or recycled, if you like, because it is a catalyst. So this is a general representation with a mechanism for the attack of the cyanide ion on aldehydes to give the corresponding cyanohydrin. These reactions are actually reversible. This is a very important note of these reactions. This reaction is more important in aldehydes than in ketones due to sterical hindrance of ketones, the less accessibility of nucleophiles on ketones relative to aldehydes, and not only that, the stability of the corresponding cyanohydrin product. If you, instead of hydrogen, now we have R, if you started with a ketone, that cyanohydrin will be more bulky relative to the aldehyde cyanohydrin, and therefore the cyanohydrin of ketones or cyanohydrins of ketones should be actually be less stable than cyanohydrins of aldehydes. Therefore, cyanohydrin formation reactions are more important in aldehydes. To conclude, aldehydes or ketones in general react with the cyanide ion in the presence of HCN to form the corresponding cyanohydrin.